Before we do, I want to remind you that the first ACM meeting is tonight at 5 o'clock. It's in actually S121, which is upstairs. If you're so inclined, you want to meet other students in CS, maybe people who have been through this part of the program already, stop by. There's pizza, which is always a good thing. You'll meet some people, and that's actually worthwhile. So, oh, now it's working. Good. So, a couple of administrative items. We start our TA help sessions and office hours next week. Those will be held over Zoom. We will publish those on the course website. I'm having a little bit of trouble getting your discussion sections to show up on the calendar. I wrote in a report to ICON to ask ICON help, so I should have that done today. Today you'll get your Lab 0. It's not due until next week, but you don't actually have to turn anything in. It's completely optional. In Lab 0, you're going to be installing Python on your machine. You're going to need a working Python implementation. There's one that's recommended in Lab 0. Those of you with Macintoshes probably have Python installed. It may well be Python 2, which will not work for this class. So my advice to you is install the Python we use for class. The version we install is something called Anaconda. It's a very complete, reasonable Python to use. It will remove one layer of complexity from having to deal with things that differ on your machine from everybody else. So people who try to use their own Python often find out there's some modules missing in whatever build they're using, and then they show up during my office hours and say, it doesn't work on my PC or my Mac. I can't help you. So my advice to you is to use Anaconda. Everything we do in class I'll have tested on Anaconda, so I'll know it works. And that just gives us all the same sort of, base system and makes things a lot easier. So turning in Lab 0 is optional. It's basically turning in a little program you'll write. The lab write-up tells you what the program should do. It tells you what the program should look like. Your job is to make it complete. And then if you upload it, you'll actually get something back from the AutoGrader. But it's just a good way to test to make sure you're comfortable using that system. Okay, so tomorrow, you're going to work on Lab 0. The TA is going to demo how to install it. If you bring your laptop, you can go along with the TA and do it on your own machine. So I'd recommend that you do that if you can. Those of you who use a desktop at home instead of a laptop, for your work, just take notes, and you'll be able to do it at home following those instructions. Okay, so every lab after this one will be handed out at the lab's discussion section. Basically, it'll be released on ICON 5 minutes before the start of session, and it will be due 5 minutes after the end of your session. You have to attend your own session because that's the assignment that will come to you. Since you're within sections, you go to another section, you won't have an assignment to work on. So you got to stick to the assigned section that you signed up for. All right, so nothing really is going to be graded in Lab 0 at all. But you do have an option to pretend to hand something in, and hand something in so you know that it works. And this just seems like, oh yeah, when you're working at home trying to get it on your own machine, if you get stuck, please post it on Piazza. I'm happy to see some of you have already started posting questions. That's great. We answer them as quickly as possible. So this is the best way to get help. And the expectation of Piazza is that answers are often crowdsourced. So because the questions are not specific to you and your work, when you write a question, I don't want to see you posting the homework solution on Piazza and saying, why doesn't this work? That's not what it's for. You can post the homework solution you're having trouble with on Piazza, but make it private to the instructors, not to everybody. It's okay to post private questions to instructors. But I hope that you'll post mostly public questions. Why was 3 + 3 = 7 in Python? And the rest of you who are reading this, feel free to contribute to the solution and the answer. That discussion board is how you learn a lot of the stuff that seems obvious to some people, less obvious to others. And it's good to have that interactive component. So I hope that we can build a sort of more healthy, conversational community on Piazza over the course of the term. The lab's going to be released this afternoon after the TAs have finished reading it. I have a TA meeting in the morning on Monday at 11, so should be up in the afternoon. Please do read it before going to the lab. All right, so let's talk about programming. All programs, any program, remember the little picture we had, gets some input, does something to it, produces some output. They all manipulate data. And data is basically some representation of the real world that you're dealing with. If you're solving the stable marriage problem, it's the preference lists of the individuals. If you're solving the scheduling problem for university classrooms, it's which classrooms you have, what their capacity are, what times classes meet, and so on. Ultimately, as you mostly know, inside the computer, everything is represented as a series of ones and zeros, as bits. And the reason that is because at the hardware level, really a computer is just a collection of interesting switches. And switches work best when you have two positions, on and off. That's not to say it's the only way to do things, but it's the way computers are built for the most part. There are variations. There are analog computers that don't represent things as quanta at all, but as continuous values. These are not the topic of this course. And in the olden days, in Germany, post-war Germany, in Russia in the 50s, people actually built ternary system computers, systems that were built of representations of 3 values rather than 2. But for the most part, computers are binary, manipulate binary digits or bits, and that's because they're made out of switches. Now, those of you who have done some programming in the past have encountered this idea of something called a data type, things like an integer, or a floating point, or a string, or a character, or even an image. And all of these things are built into the language that you're using. So if you're using C, then you have this notion of a short integer and a long integer. If you're using, I don't know, name a language, it'll have its own collection of data types that are built into the language and allow you to represent data of different types. And the question is, if everything is made out of bits, why do languages have data types at all? And the answer to that is that, again, in the olden days, the early days of computing, there were no higher level languages. People simply wrote in machine language, the language specific to the hardware that you bought. You buy an IBM something something machine, it comes with an instruction set. You write your code for that machine using that instruction set. You decide how to represent a string or how to represent an occupied classroom. That's up to you. That machine breaks, or there's a new fancy machine that you buy to replace it. Your programs go out the window, and you rewrite them for the new machine instruction set. The thing that made IBM a great company in the 50s was that they sold machines across they didn't actually sell them, they rented machines across the spectrum. You could have a small IBM machine, and when your business grew, you could trade it in and lease a larger IBM machine, and they shared the same underlying architecture, which meant you didn't have to throw your software out. So programming languages give you that handy layer of abstraction. Now I'm not writing in the language for my IBM 3060. I'm writing in a language that works on the IBM 3060, but also runs on my Android phone. So these programming languages and their abstract data types give us the ability to write code that is more portable. That was a big deal in the 60s, before any of you were born. So in the old days, with machine instructions, I have a 1 and a 0. I can decide the 1 means true and the 0 means false. I could decide the 0 means true and the 1 means false. It's completely up to me. I'm writing the code. I get to decide. The beauty of these higher level languages, like Python and all the other languages you can think of, is that they adopt a set of meaningful conventions, sometimes shared across multiple languages, so that I don't have to worry about the 1s and the 0s. I want to represent true, call it true. I want to represent an image, there's a way of doing that. I want to represent a string of characters, there's a way of doing that. And all of these languages have these conventions that attribute meaning to collections of bits. So for example, an integer is a collection of 64 bits that can represent numbers from 0 to 2 to the 64th minus 1. So there's this sort of range of representations, and that's considered standard within the language. Now, they're not always the same. I mentioned the other day that computer scientists like to start counting from 0. In some languages, the first element of an array is the 0th element. That's the way it is in Python. In other languages, the first element of the array is the first element. So there are inconsistencies across languages and families of languages. But within a language, the data types that are built in, they give you the tools to represent data that you're going to compute with. So the first thing we're going to do in this class is we're going to go through the data types in Python to some fairly detailed degree so that you understand which one is appropriate to use when and how they each individually work. Now what's cool about these is that each one of these data types gives us some convention for the internal bit representation of that type of data. What is an integer really? What is a floating point number really? But they also provide, sort of packaged with that data type, a collection of operations that you can do on that type of data. And again, those collections of operations, they're pretty standard. You're always going to want to add integers together, for example, or divide one from the other, or subtract, or take 1 over something. Those are kind of standard operations that you have to have. But they are also slightly different from one language to the next. Not the operations themselves, but their behavior, especially in what are called edge cases, situations that aren't obvious. So that's why we're going to spend some time going over these in Python. So the primitive data types hide the ugliness of the bit representation and the operations on those bits. They come with these set of operations like addition, subtraction, concatenation, indexing, and so on. We're going to spend about 3 weeks in this class going through a collection of data types in Python. What distinguishes Python from a lot of other languages is it's got a really cool set of built-in data types. If I were teaching this class 20 years ago, I'd probably be lecturing on ANSI C, which has essentially 2 data types. Everything else you have to make up on your own. You want a linked list? You got to design and implement that abstract data type. You want an associative array? You got to implement it. In Python, you get all that stuff for free. And it's well written and robust, and it's error-free. So this is a huge win for getting something to work quickly. Now, once I have my built-in data types, I can build more complicated data types that are suitable for whatever you're working on by making combinations, custom combinations of the built-in ones that I have. So I'm writing a program to schedule classroom use. I'm going to have something that represents a student. What represents a student? Student is represented by a first name, a last name, a student identifier, a home address, a zip code, a grade point average, a collection of classes they've taken. All those things are primitive data types, but the collection of them configured in a certain way can be used to represent a student in my classroom scheduling system. So we'll start with the basics, the built-in types, and throughout the course of the semester we'll build more complex types out of those. I'm going to mention a little bit here this notion of something that's dynamically typed. Who's heard this term before? Okay, so this is a big deal in programming language design, and I'm going to try to set you up so you understand the difference between a language like Python and a language like C or C++. Some of you probably have C++. Python is a dynamically typed language. That means when I create a variable, which is just a name for a piece of data, when I have a variable that stands for a student, x equals Hunter? Is that Hunter? Trevor, sorry. X equals Trevor. Then there's a representation for Trevor, but I'm just going to carry around this label X so that I can say X represents Trevor. I'm going to give him an A, so I'm going to make a change to X. In most languages, the older languages, when I create a variable called x, I have to decide a priori, is x going to be an integer? Is x going to be a floating point number? Is x going to be an array of integers, for example? And once I decide the type of x, meaning what data types it can be matched to, that's fixed for all time. In Python and some other languages, x can start out as an integer, but later it could change to a string of characters, or maybe an array of numbers. So in Python's case, variables can change their type whenever you want. Now that's both good. Why is it good? Because it means you don't have to bother to sit there and decide what type the variable is when you write the code and make sure you respect the variable and so on. But also bad. Why is it bad? Well, first of all, the code's a little less efficient because it doesn't know the type at compile time. But secondly, and more importantly, this is a case where Python gives you enough rope to hang yourself. Right? It gives you great flexibility, but with great flexibility comes great responsibility on the part of the programmer. And this is why I drill people so much on data types, making you think what this thing is and how it's represented. Because as you write your code, it's up to you to keep in mind what x really is. Because if you forget, you're going to start doing things to x that x doesn't want you to do. And then you're going to have some errors and your program's going to break. So we'll talk about this some more later, but I want to introduce the term now. Okay, let's go over the standard data types for Python. We have numeric types, which you've probably seen in other languages: integer, whole numbers, floating point numbers, numbers with a decimal point in them, complex numbers, just like you have in trigonometry, right? I am bold-facing the ones that we're actually going to talk about individually. Numbers like complex, I'm not going to talk about that. It's in your reading. There's a whole chapter that goes over these types. I'll leave that to you. But we're going to go through the bold-faced ones on our own. Logical types. There's a logical type called Booleans. Talk about those. They're important. We'll talk about sequence types. There's a lot of these in Python. Strings are sequence types. Bytes, byte arrays, lists, tuples, and ranges are all sequence types. Sequence types are collections of items that have an intrinsic ordering. All right? So the class list that I have for you is a sequence of data, the data being each of your student records, and there's an implicit ordering, usually alphabetical by last name. This is a sequence type. We're talking about mapping types, dictionaries. Mapping types are collections of objects where there is no implicit ordering. But there is a mapping from one thing to another, an index to a value. We'll talk about set types, set and frozen set. Set types are also collections of values where there is no intrinsic ordering in sets. And each one of these data types comes bundled with its operations on those types. So as we go through the types, I'll introduce those operations. We'll see how they work, and you'll get some familiarity with building programs that basically directly manipulate data. Later, we'll talk about more complicated types. We'll talk about objects, functions, methods, modules, and classes. These are all abstractions of types. It's this whole hierarchy of types. We'll start with the built-in ones, and we'll talk about the other ones later. Of course, all of these things inside the computer are still just collections of bits. So if you think of a set data type, which is a collection, think of the set of all first names in this class. It's a set of strings, where the string is your first name. It's a big set, almost as big as the class. Certainly no bigger, possibly smaller if there are two Joes in the class. But it's a set of strings. Each of those strings is represented as a collection of bits. And the collection of those bit collections is also represented as a collection of bits. And what these data types and their operations do is they let me not think about the bits and just think about the things I'm representing. Other questions? Is that sort of clear? You still with me? Bored yet? Not yet? You get sick of me soon enough. My daughters say, oh God, he's going to lecture again. So I'm digressing. I'm going to miss class one Friday in April because my daughter's getting married April 16th, my oldest. And my wife's already started saying, the father of the bride gives a toast. She says, it's not a lecture. You don't get to have a syllabus for the bridal toast. So I've got to work on that, and I've been cautioned about talking too much at the wedding. I'll show you pictures when I get back. I'm sure I'm going to be in trouble. By the way, getting married is really expensive. Holy smokes. It's just not what you think of. It's like pretty much like half a house to get married. It's just crazy. All right, back on topic. Start with our very first types, numeric types. I'm going to talk about the integer data type, which is used to represent whole numbers. What do I mean by whole numbers? Numbers that don't have a decimal point. Things that we can use to count things. There are 188 students in this class, not 188.3. I have two daughters, not 2.0 daughters. Whole numbers. They can be positive, they can be negative, and they include the number 0. Now, legal integers are input to Python with a set of typed characters that define that integer. So let's talk about how that integer might look like. There's an optional plus or minus sign. You cannot include that, and then it defaults to plus. Followed by directly, no spaces, directly by a series of one or more digits from this set of digits. All of these assume that you're talking base 10. You remember from grade school when you had to learn like about base 8 and base 6 and base 5? That's actually a thing. We're going to use that. Here we're going to assume that this is base 10 interpretation. And because it's a base 10 interpretation, with the exception of the integer value 0, you are not allowed to start an integer with a 0. In other words, you can't type 0, 1, 0. You type just 1, 0 for 10. You can't type minus 0, 3, 3 for negative 33. It's just minus 33. You can, however, type 0 because there's no other way of saying the number 0. For other bases, octal and hexadecimal come to mind. When we're typing octal or hexadecimal values, which is common in computing, we need a little bit of notational syntactic sugar, it's called, to be able to say, hey, this number that looks like a 12 is really not a 12. It's a 10 in base 8. So I need to have some way of saying this next set of digits that look like they're decimal, they're not decimal, they're octal. So to do that, we're going to have to extend our notion of this representation, and we'll do that later today. Now, here's one of the cool things about Python. In every other language you've probably written in, you know that there's something called the maxint value. What is the largest integer you can represent? In some languages, when you exceed that value, it automatically changes to exponential notation. So your numbers get bigger and bigger and bigger. All of a sudden, it's 13.65273 times 10 to the 12th. Because the numbers exceeded our representational capacity of ones and zeros. How many of you have seen that before, had that experience? So here's what's cool about Python. In Python, there is no arbitrary size limit to integers. You can type the biggest integer you want, and it'll always show up like an integer. Technically, we say these are unboxed integers. You don't need to care. You just need to know that that major pain in the patootie thing about having the smallest possible integer, most negative number, and the largest possible integer, most positive number, that you have in other languages, that disappears in Python. We'll see examples later. Okay, so talked about our first data type. Let's test it out. To do that, we're going to open a Python session, which you'll see referred to as a REPL. A REPL is a read, eval, print loop. Fundamentally, Python is an interactive language, unlike many other languages, where you can actually type stuff to Python and have it evaluate it right away. You can use Python like the world's best giant calculator. And in fact, I don't use a calculator on my cell phone. I have a little Python implementation. I can open it I can type my expression and I can get a value using the Python read-eval print loop. So the read-eval print loop is the interactive session with Python that essentially reads an input, evaluates it, prints the value, and then does this over and over and over again. So the REPL is called a REPL because that's exactly what it does. So let's see what it looks like. In each step, Python reads the expression you type, which for integers should look like an optional plus or minus followed by a series of digits. It will report an error in syntax right away. If you type 020, it's going to say, I can't do that. If you type 20, it's fine. And then it's going to evaluate that thing and echo it back to you. So what's cool here is that in the evaluation step, the evaluation can be very simple, or it can be extremely complicated. It can involve large calculations, or it can just involve saying back to you, yeah, I get it, 20 is 20. Here's 20. In the evaluation step, as we evaluate the expression, we cache the results in memory. We report errors in semantics. What's an error in semantics versus an error in syntax? An error in syntax is something you type that is not well formed according to the rules of how you express integers. So 020 is a good example of something that is a syntactic error. An error in semantics, the difference between syntax comes from the word for form. It's how you express something. The semantics are the meaning of the thing you express. An error in semantics is something like, I typed this big expression and it ends up being a divide by 0. Divide by 0 is an error in meaning. It's undefined. So as I type in the expression, Python will tell me about syntax errors. Once I've typed it in and Python tries to evaluate it, it will report semantic errors. And those are the things that you have to correct to make Python work correctly. Finally, in the print step, the result of the evaluated expression is interpreted in a way that Python can print it out, and it prints it out. Remember, internally, Python's doing ones and zeros. If I type a complicated expression that evaluates to the number 7, Python has nowhere in its memory a 7. What it has in its memory is a pattern of bits that, interpreted by the right data type machinery, means 7. And in the print step, Python looks at that and generates a printed representation for us dummies who can't understand the direct binary representation. Okay, so let's see some examples. Python, you get a prompt. It's a triple caret or triple greater than. You type to that and hit return and evaluates it. So when I start up my Python, this is an older version of Anaconda. It tells me it's Anaconda, and I get the license and so on, and then I get the prompt. When you install Anaconda on your machine, it'll be version 3.9.4, but by and large it's the same. Okay, if I type 0 to Python, first of all, is that a well-formed expression? Syntactically, does 0 have meaning? And the answer is yes. It stands for the integer number that has 0 value. If I hit return, Python will look at that, evaluate it. In the absence of a syntax error, it will interpret it. Oh, that's the integer 0. It will represent it in memory, and then it'll say, okay, that's the result of this evaluation is 0. Let me build a printed representation that I can print out for the dummy who types 0 to the prompt. And I get it right back, followed by the loop part as the new prompt. Right? Easy, right? So you're typing to Python and it's evaluating and responding. If I type the integer 134, I get back 134. If I type the integer negative 46, I get back negative 46. This isn't rocket science, right? It doesn't seem like it's doing anything, but actually Python's doing a lot behind the scenes. So consider what happens if I type minus 0. So first of all, is minus 0 legal integer representation? Well, I told you the rules, plus or minus optional, followed by a sequence of 0 through 9s. So to me, that looks like a optional minus followed by a 0. Python reads that in, evaluates it to create a unique interpretation of the semantics of what I typed, which is, by the way, what number? So 0, right? And then it generates a printed representation of 0 that looks like that. So what happened to the minus sign? Well, the minus sign doesn't really change the meaning of that 0. And the printed representation of Python generates a canonical version of what its meaning is. So even something as simple as typing a number involves all this Python machinery to interpret it, build a unique semantic interpretation, a unique internal representation of that thing, which then you throw all of this stuff away to keep that internal representation. And when you hit return, you look at the internal representation, and Python generates a canonical representation for you, which is this. Not minus 0, just 0. Okay? So a lot of stuff going on. What about something like that? Well, sure looks like a number, looks like a power of 2 to the 10th, right? But actually, this is a syntactical error. It's a syntax error because Python does not allow integers to use the column separating comma. When I told you how to type an integer, I didn't tell you you can use commas. I told you it's a plus or minus optional, followed by a series of 0 through 9s. That comma doesn't have any meaning to Python. So it generates this syntax error, shows me where the error is, and invalid token, in this case, is referring to the comma sign. Well, here's the thing I promised you, 020. When I type that, Python gives me a syntax error because we're not allowed to use a leading 0 in an integer. The only 0 we're allowed to use first is for that number and that number alone. So what's going on here, and why this veto on leading zeros? Well, the answer is pretty simple. In Python 2, this is Python 3, in Python 2, a leading 0 meant the next integer that starts with leading 0 is not in base 10. It's in base 8, octal. Now that's a little bit weird because, you know, it's not inconceivable that I might type a number with a leading 0 by mistake, thinking it's base 10, and Python would silently interpret it as an octal number and give me an answer that didn't make any sense. So when we updated from Python 2 to Python 3, now probably, I don't know, 7, 8 years ago, maybe more, I lose count. One of the things they got rid of was this notion of using a leading 0 to represent octal in Python. We now have a different, I called it notational jujitsu or syntactic sugar. There's now a differential syntactic sugar to indicate an octal input or a hexadecimal input, and I'll show you that in a minute. But because people were used to typing this, they've decided that this should now throw an error. So if you try to pass something off as an octal in Python 3 with a leading 0, you get an error. If you mistakenly type a decimal number with a leading 0, you get the same error, and that's okay. So here's another example. Here I have a 0 with a lowercase o 20 plus a 0 with a lowercase x 10. Now, I'll tell you now that the O, 0O, is Python 3's way of saying that this is an octal number. So 0O20 means that it's the 20 octal, which means it's 2 times 8 and 0 times 1, or 16. So this number stands for 16. The lowercase x is Python 3's way of saying that this number is actually hexadecimal. Hexadecimal is base 16. In base 16, we use the numbers, the digits 0 through 9, plus the letters A through F to get 16 symbols. Here I have a 1 in the 16s position. So this hexadecimal number is 16. The octal number is 16. And for the first time, I'm using an operation that's defined on integers. Remember, these are octal and hexadecimal representations, but they're still just integers, whole numbers. So the net result here is that 16 in octal plus 16 in hexadecimal produces 32 in decimal. Now, this is a stupid example. But I want you to remember, when you type to the read-eval print loop, there's a lot of stuff going on behind the scenes. I'm interpreting everything, Python's interpreting everything and saying, is that a legal input representation? What does it mean? It's constructing the internal meaning, which is 16 and 16. It's applying the operations on integers to add them together. And then when it ends up with the representation of 32, it's deciding how to print that out so that you will understand it. And the canonical means is to print out a decimal number. All right? Yes?
Is it just printing out in base 10 because the two numbers are in different bases?
Nope, it's a convention as output is in base 10. So the read-eval print loop is for people. And people in general, don't do this, right? So it's base 10 by convention. Good question. Anybody else? We have clock disagreement. Okay, more operations on integers. Here's another input. I have a 3 plus a plus 4. Well, this plus here is different than this plus here. This plus here is part of the input convention for this integer. So this is a positive number 3 plus a positive number 4, and the answer will be 7. But the same basic rules apply. Read in the tokens, decide what they mean, apply the operations to those tokens, find the result in memory, print out a printed version of that result. 3 asterisk 4 in Python, like most languages, the asterisk is multiplication. I get 12. Minus 3, again, the leading minus says this is a negative number. Minus 3 is going to be minus 6. Minus 3 / 3. Now this is interesting. This is a difference from Python 2 and Python 3. Python 3 has the more rational, well-formed integer operations. The // is the division operation. But unlike in other languages, Python has 2 different division operations. It has a division operation defined for integers and a division operation defined for floating point numbers, which we'll see shortly. The // is integer division. And what that means is that when I divide this integer by this integer, the result I get will always be an integer. So when you do integer division, 4 integer divided by 3, you have a division and a remainder. So let's see that. So the operator here, the percent sign, is the corresponding remainder operation for the integer divide. So minus 3 divided by 3, integer, is a minus 1, with a remainder of 0, because 3 divides minus 3 evenly. So when I do integer division on integers, I not only get an integer back, but I can separately recover the remainder part of that division. Minus 3 divided by 3 now, this division is a single slash. That is not integer division. It's a different type of division that in this case gives me the same number, but you'll notice that it added a decimal 0. This number is not an integer. This division is a floating point division operation. It does decimal division the way you would expect it to be done. So 4 divided by 3 is not going to be 1 unless you do integer division. With floating point division, it'll be 1.33, so on. So that's not an integer. That's actually floating point. So let's see what this looks like. With 4 divided by 3, we're going to get this 1.3 out to some precision. Now this precision that I'm seeing here is imposed at the time of printout. So remember, I input these numbers, and Python builds a representation internally of what this number is. Happens to be a floating point number. And then in the last step, to print it out for us dummies, it looks at that number and says, what's the printed representation for this number? And it comes up with this, 1.33, like 12 of these. Now this clearly is a repeating 3, because we all know that from grade school, right? It's a repeating 3, but somewhere it stops because it doesn't want to print it out forever. That's an artifact of the printing part of this operation, not of the internal representation. For all we know, internally, this may not have that repeating irrational part to it. Because remember, internally, we're not in base 10 anymore. We're in base 2. Numbers that in base 10 can be divided normally, internally in base 2, sometimes have that repeating character. So remember that this precision approximation here is an artifact of the printing part of Python that looks at the internal representation and produces a written one. That can sometimes fool you. If I do integer division, of course, I only get the integer part of the divide, and I have to recover the remainder part, also called the modulus, using the other operation. So the way to determine this is 4 is equal to 1 times 3 plus 1. Okay, more operations. The double asterisk is exponentiation in Python, like in many other languages. So I want to take 34,566 raised to the 45th power. I can do that in Python with the double asterisk. And here's where Python's magic comes through. I get back an integer. It's integer exponentiation. I get back an integer that is really quite long. Try this in most languages you've used before, and you'll get back something in exponential notation. Not in Python. Integers are on box. Arbitrary precision integers always. That is a cool thing. It makes it easy to work with integer rather than have to worry about what's the largest representation. Do I have to normalize what's the loss of precision? It's arbitrary precision arithmetic for all integers. Okay. Questions? So I have quarter after, so 5 more minutes. So let's push on a little bit more and see how far we get today, and then we can stop for the day. Okay, so you've seen integers. We've hinted at floating point numbers, although we haven't really talked about them very much. You've seen some operations on integers. But the whole point of having a language with built-in types is that not only do you have the obvious operations like plus and minus and divide, but there are other types of operations, functions in this case, that work on those same data types. So for example, this is a Python function called max. It's a built-in function. It takes 2 arguments, and it returns whichever one of those 2 is greater. So on integers, max 3, 4 will return 4. It's a similar function called min, which will return the other one, the smaller one of the 2. When I do min with negative numbers, of course, I'll get the more negative one. If I add the minimum of these 2 numbers and the maximum of these 2 numbers, I evaluate this function to get minus 1. I evaluate this function to get 1. I add minus 1 and 1 to get 0 inside Python. And when I print that representation, I get the 0. So even in this simple example, we learn one thing. You've already seen operations on numbers with plus signs and exponentiation and modulus, integer divide and divide. But now we have this other kind of thing called a function. And functions in Python always have a name of that function, which is some character string representation. Sometimes that name can be quite complicated. But for now, we'll stick to simple functions. Followed by 2 parentheses and a collection, these are called arguments, inside the parentheses separated by commas. So in the case of max and min, these are functions that take 2 arguments separated by a comma. And the way I interpret these arguments is Python looks at this. It starts with the first argument, evaluates that, which is just a 3. Evaluates the second argument, which is just a 4. And then takes these 2 evaluated operands and passes them to the function, does the computation, and stores the result in memory. And then the read eval print loop takes that result and by magic turns it into a printed representation. So function evaluation is kind of the fundamental thing we do in Python. We will be defining new functions, and we will be invoking those functions to compute new stuff. Some of these functions, like max and min, will be built in. Others will be functions we ourselves will define. So the function invocation itself, like this one, or this one here, min and max, they actually stand in for a value. So when I type this expression, I'm saying whatever the result of this function invocation is, gets added to whatever the result of that function invocation is. And because I don't know the results of those invocations, I must do that first. So when Python evaluates this expression, in a sense, it evaluates it from the inside out. It first evaluates the min. To evaluate the min, it needs to evaluate the first operand, then the second operand, and then it evaluates min and comes up with a result. Does the same thing for max, and only when it's done all that can it add them together to get our final result. Okay, are we clear on the way function evaluation works? I mean, it's kind of like you had in your, if you had one of those calculators where you could type expressions in high school, same thing, right? Just the rules are a little more specific in Python. So I will stop with this next slide. The whole idea of programming in Python is largely comes down to extending the language you've been given. So I hand you Python, which you'll install tomorrow. It comes with all these built-in data types and their operands and their functions that are built in, like max and min. And you're going to create new functions that you're going to add to the system. That's what programming is. You define functions. And the function definition looks like this. You'll use the Python keyword def in front of the function name, and then 2 parentheses including the parameter definitions for that function, and a trailing colon. And then what you have inside the body of the function is tab-indented series of statements that often, but not always, end with a return statement containing whatever the value you've computed here should look like. And we're going to pick this up on Wednesday as we start to define our own functions, for starters, just on integers. Okay, I'll see you. Don't forget your discussion section tomorrow. Read Lab 0 will be up on the website sometime today. Questions, go to Piazza, and we'll see you on Wednesday.